all my viewers, feel most welcome into our today's discussion, whereby we are going to discuss about the inverse Laplace transform. When you've been given a function like this one to find its inverse Laplace transform, the first thing that you must check on is on the denominator. And is on the denominator. For a function like this one, we understand that we must use the complete square method. When it comes to the complete square method, denominator s squared, we subtract from 4s, we subtract from 5 is going to be equals to 0. We take this 5 on the other side since we are going to use the complete square in solving our denominator. So we are going to have s squared, we subtract from 4s is going to be equals to a negative of 5. For a complete square to be, for a linear equation to be complete, we understand that we must have our term of c. Here we are not having our term of c. We must now introduce the term of c. And how are we going to introduce our term of c? We are going to have c is equals to b all over 2 everything squared, to mean that our term of b is equals to negative 4. Now we are going to have negative 4 all over 2 everything need to be squared, to mean that here we can simplify and say negative 2 squared. This is now our term of c. We can now rewrite everything and say s squared, we subtract from 4s, we add 2, negative 2 squared is equals, will be equals to negative 5, we add 2, negative 2, everything squared. From this point now, we collect the like terms. And by the like terms, this is what I mean. When you check here, we are having the terms of power of 2. To mean that now we are going to have s, we subtract from 2, but they have a common term of squared on them. On this side, we can just simplify everything and we are going to have negative 5. Here we are going to have a positive of 4, to mean that we are going to have a negative of 1. We can now rearrange everything and say s, when we subtract from 2 squared, now we are going to add to 1. And this is how you go about our denominator here. Now we can come and rewrite everything and say the inverse Laplace transform of 4s, we subtract from 3 all over s, we subtract from 2 squared, we come and add to 1. Whatever we are having on this point is equals to whatever we are having here. Let us now start our working here. After rewriting the denominator, when we check the term of s, it has been shifted, to mean that here also we must shift our term of s. By shifting this term, we are going to relate whatever we are having here with whatever we are having on the numerator. And how are we going to relate these two? We are going to have s, we subtract from 2 because the term of s was shifted. We come and add to a, it will be equals to our numerator 4s we subtract from 3. When we check at the coefficient of s here, it is equals to 4, to mean that we come and introduce here 4. Let us now get the value of a. We are going to have 4s we subtract from 8. We add to a, everything is equals to 4s we subtract from 3. Here we are having a positive of 4s, and here we are having a positive of 4s. When you collect those terms together, they are going to cancel out, and we will be having 8. We add to a is equals to negative 3. A is equals to, when we take this a to the other side, we are going to have a positive of 5. From this point now, we can rewrite our numerator as the Laplace inverse of 4 into s we subtract from 2. We come and now add to a all over s we subtract from 2, everything now squared, we add to 1. This is how we can rewrite our numerator and relate to the shifting method. But our value of a was equals to 5, to mean that the inverse now Laplace transform of 4 into s we subtract from 2. We come and add to, here we are having a positive of 5 all over s we subtract from 2, everything squared, we come and add to 1. From this point now, we can come and have two separate inverse equations, and this is how we are going to have them. The inverse Laplace transform of 4 into s we subtract from 2 all over s we subtract from 2 squared, we are going to add to 1. We come and add to the inverse Laplace transform of 5 all over s we subtract from 2, everything squared, we come and add to 1. This is how we can write our function from this point, by expanding those two inverse equations. Let us now find the Laplace inverse of these two. We understand that from the first shift theorem, we understand that exponential positive or negative of at cos our angle t is equals to, here we are going to, here first you must get the Laplace transform of cos our angle t, whereby we are going to have s all over s squared, we add to our angle squared. But since we are using the first shift theorem, it means that the term of s must be shifted, and when we shift here, we are going to have s negative or positive of a. Also on the denominator, we are going to have s negative or positive of a squared. Let us check on the sign. These ones are the Laplace transform of this function. The Laplace transform of at sine our angle t will be equals to our angle lambda all over the Laplace transform of this function is equals to s squared. We come and add to our angle squared. But since we are carrying out the first shift theorem, it means that the term of s must be shifted, and here we are going to have s negative or positive of a, everything squared. This is how we do the first shift theorem. To mean that now here we are going to have for the inverse Laplace transform of s we subtract from 2 all over s we subtract from 2 everything squared, we add to 1, and here we are going to have, we add to 5, the inverse Laplace transform of 1 all over s we subtract from 2 squared, we come and add to 1. We understand that 1 squared is equals to 1. It doesn't have any effect. Let us now get into our first function here. When we check out this function, we are having the term of s being shifted on the numerator and the denominator to mean that it resembles this function here. Now we are moving from this point back to this point. So it is very important for you to understand the first shift theorem. You can check on the videos that I've done on the first shift theorem. And now from this point, now we are going to have for exponential here, the term of a is a negative of 2. We say that when we are having a negative here, the exponential is going to take a positive of 2a, to mean that here we are going to have 2t, because a stands for the exponential power here. Cos our angle squared here, we say that it is now going to be 1, which is going to be equals to t. We come and add to 5 exponential here. Our angle, a, here it was shifted with respect to a negative of 2t, to mean that we are going to have a positive of 2t sine t, because our angle is equals to 1. And that is how you relate whatever we are having here and its inverse Laplace transform, to mean that the inverse Laplace transform of this function is equals to whatever we are having here. Thank you for your time. Let us now meet in my next example, whereby I'm still going to discuss about the inverse Laplace transform.